Welcome to the Sleepy Scholar. It's lovely to have you here tonight, whoever you are, wherever you happen to be lying right now. Maybe you're under a heavy blanket with just one lamp still glowing in the corner. Maybe you're on a couch that has slowly become a bed, the way couches do late in the evening. Maybe you're on a train or a long drive as a passenger, watching the dark slide by. Wherever you are, and whatever time it is in your corner of the world, I'm glad you found your way here. Settle in. Let your shoulders drop. There is nowhere you need to be, and nothing you need to solve for as long as this lasts. So, before we begin, let me tell you what tonight is going to be. We're going to drift, very slowly, out past everything familiar. Past the walls of your room, past the roof, past the clouds if there are any tonight, past the moon and past the planets, and past every single star you have ever seen with your own eyes. We're going to leave our whole galaxy behind us, all of it, every star in the Milky Way, and we're going to travel until we reach another galaxy entirely. And there, in that distant place, we're going to look at something that, until recently, almost nobody believed could ever be found. A planet. A single, faraway world, possibly circling a dead star, in a galaxy so far away that the light leaving it tonight will not reach a future stargazer for millions of years. I'll try, as I always do, not to make this so interesting that it keeps you awake. But if it does, well, at least you'll have learnt something lovely on the way. A fair trade, I think. And if you drift off before the end, that's perfectly fine. That's the whole idea, really. The story will still be here. The planet will still be there. You lose nothing by letting go. And if you enjoy these slow journeys, and you'd like more nights like this one, a gentle like and subscribe really does help this sleepy little channel keep going. Small creators like me rely on that more than you might think. And to those of you already subscribed, already part of this quiet little ritual, thank you, truly. You're the reason the lamp stays on. Before we set off, I'd love to know, in a soft way, no rush, where in the world you're listening from tonight. Leave it in the comments if you feel like it. Your town, your city, the time on your clock. It's nice to imagine all of us drifting off under the same sky, just from different corners of it. Now, let's begin, shall we? I want you to picture the number first, before anything else. Just the number, held gently in your mind like a smooth stone in your palm. 28 million. 28 million light years. That's the distance we're talking about tonight. Not miles, not kilometers, but light years, and each light year is already almost too big to hold. A light year is how far light travels in one whole year, and light is the fastest thing there is. In a single second, light could circle the Earth several times over. Let it run for a year without stopping, and it crosses a distance so vast we had to invent a new word just to talk about it. And now take that already enormous distance and multiply it by 28 million. That is how far away the thing we're going to talk about tonight actually is. For almost all of human history, we knew of exactly one world that could hold life, and that was our own. Then, slowly, we found the other planets in our own solar system. Then, much later, in the last few decades, we began to find planets around other stars. We call those exoplanets, which just means planets outside our own solar system, orbiting suns that are not our sun. And we found a lot of them, thousands, more than 5,000 confirmed, at the last real count, and more arriving all the time. Worlds of every kind, giants bigger than Jupiter. Small rocky places, worlds so close to their stars that a year lasts only hours, and worlds so far out that they drift in near permanent cold. But here is the thing that I want you to hold on to, softly, as you lie there. Every single one of those thousands of planets, all 5,000 and more, has one thing in common. Every one of them lives inside our galaxy, inside the Milky Way. They are scattered around us, some near, some far, but all of them within a few thousand light years. Which sounds enormous, and is, but on the scale of the whole universe is really just our own neighborhood, our own little patch of the cosmic city. We had never, not once, found a planet outside the Milky Way. Not one. The galaxies beyond ours were, for the purpose of planet hunting, simply too far. Too far to see anything so small as a world. It seemed, honestly, like a door that would never open. And then, in September of 2021, a team of astronomers announced something that made a great many people sit up in their chairs. They had found a candidate, a possible planet, not in our galaxy, in another one entirely. 28 million light-years away. Let that settle for a moment. No need to rush past it. For the very first time, someone had reason to believe they had spotted a world outside the Milky Way. A planet in a completely different galaxy. If it's real, and we'll talk about that if very carefully, because honesty matters here, then it pushes the boundary of where we've ever found a planet outward by something like 10,000 times. 10,000 times farther than any planet we'd found before. That's the kind of leap that doesn't happen often. That's the kind of leap that rewrites the edge of the map. The planet has a name, though it isn't a pretty one. Scientists tend to name things by where they are and how they were found, rather than by how they sound. This one is called M51 ULS 1b. I'll say it again slowly, so it can just wash over you without any pressure to remember it. M51 ULS 1b. Each piece of that name is a little clue about the story, and we'll unwrap each piece as we go, gently, like unfolding a letter you're in no hurry to finish. For now, just let it be a set of soft syllables. M51 ULS 1b. The first planet ever, maybe, found outside our own galaxy. Now the M51 at the front of that name tells us where it lives, and where it lives is a place you may actually have seen a picture of, even if you didn't know its name. M51 is the catalogue number for a galaxy that most people simply call the Whirlpool. The Whirlpool Galaxy. It also goes by Messier 51 and by another catalogue number, NGC 5194, but Whirlpool is the name that fits it best, because that is exactly what it looks like. A whirlpool of stars. If you have ever seen a photograph of a galaxy that looks like a perfect spiral, two grand glowing arms sweeping around a bright centre, curling like cream stirred slowly into coffee, there's a very good chance you were looking at the Whirlpool. It is, by many accounts, the most beautiful spiral galaxy in the sky. The one that ends up on posters and book covers. The textbook example of what a spiral galaxy is supposed to look like. And that is where this faraway planet is thought to live. Somewhere inside that gorgeous, spinning pinwheel of light. 28 million light-years from your bed. Now you might already be feeling the first little tug of a question. It's the same question that the astronomers themselves had to face. The same question anyone with a curious mind arrives at almost immediately. And it's this: how? How on Earth, or rather how from Earth, could anyone possibly see a planet that far away? We struggle to see planets around stars in our own galaxy, stars that are practically our next-door neighbours on the cosmic scale. Planets are small. They're dark. They don't shine with their own light the way stars do. They only reflect a little of their star's light, like a pebble catching the glow of a street lamp. And a pebble beside a searchlight is hard enough to notice from across the street. How could you possibly notice it from 28 million light-years away, across the gulf between two galaxies? That's the real mystery of tonight. And the answer is genuinely strange and genuinely beautiful, and I want to walk you through it slowly. Because it's the kind of clever that makes you smile when it finally clicks. So don't worry about grasping it all at once. We'll take it one soft step at a time. The first thing to understand is that they did not see the planet at all. Not directly. Nobody took a photograph of this world. Nobody caught its reflected light. In fact, the way they found it has nothing to do with light the planet gives off or bounces back. They found it because of a shadow. Because of something the planet blocked. They didn't see the world itself. They saw the darkness it cast as it passed in front of something bright. Think of it like this, in the gentlest way. Imagine you're sitting in a dim room at night, and there's a candle burning across the room from you. You're not looking at anything in particular, just watching that little flame. And then, for a few moments, the flame vanishes. It doesn't flicker. It doesn't dim slowly. It just cleanly goes out, as if something passed between you and it. And then, a little while later, it comes back, exactly as it was. You never saw the thing that passed by. It was too dark, too quiet. But you know something crossed in front of the candle, because for those few moments the light was gone. You saw the shadow, not the object. You inferred the moth by the darkness it made. That, at its heart, is what happened here. Astronomers were watching a source of light, a very particular and very unusual source of light in that faraway galaxy. And for about 3 hours, that light dropped away to nothing. A total blackout. Not a slight dip. Not a partial fade. The brightness fell all the way to 0, stayed there for around 3 hours, and then climbed smoothly back up to where it had been. Something had passed in front of it. Something had blocked it completely. And when the astronomers studied exactly how the light disappeared and returned, the shape of that blackout, they realized it looked precisely like what you'd expect if a planet roughly the size of Saturn had drifted across the face of that light. A 3-hour eclipse, 28 million light-years away. That was the whole discovery. That was the shadow that opened the door. Now, I told you the light they were watching was unusual, and here is where it gets genuinely strange, in the loveliest way. Because the light they were watching wasn't ordinary light at all. It wasn't the visible light you and I see, the light of a lamp or a star or the moon. It was X-ray light. The same kind of light a hospital uses to look at the bones inside you. It turns out the universe makes X-rays too, in certain violent and extreme places, and one of the tools we've built can see them from very, very far away. That tool is a telescope, but not a telescope like the ones you picture on a hilltop, with someone squinting through the eyepiece. This one doesn't sit on the ground at all. It flies in space, high above the Earth, looping around our planet. It's called the Chandra X-ray Observatory. It belongs to NASA, and it was launched all the way back in 1999. For more than 2 decades now, it has been drifting up there in the dark, its patient eye tuned not to visible light, but to X-rays, watching the most extreme objects in the universe. Exploded stars, swirling gas falling into black holes, the hot, violent corners of the cosmos that our ordinary eyes could never see. And Chandra sees them with remarkable sharpness. It can pick out individual sources of X-rays, even in other galaxies, which is an astonishing thing when you sit with it. From up there above our air, it can look 28 million light-years away and separate one bright X-ray point from another. the way you might pick out a single distant lighthouse along a far shoreline. So it was Chandra that was watching. Chandra, quietly gathering X-rays from the Whirlpool Galaxy, that recorded the 3-hour blackout. That caught the shadow, that noticed the light go all the way out and then come all the way back. And the person who led the team that made sense of it, who took that strange dip in the data and followed it all the way to a possible planet, was an astronomer named Rosanne Di Stefano. She works at the Harvard-Smithsonian Center for Astrophysics, which is one of the great homes of astronomy in the world, a place where people spend their lives asking exactly these kinds of enormous, patient questions. Di Stefano and her team took this 3-hour eclipse, studied it from every angle they could think of, and published their findings in September of 2021 in a journal called Nature Astronomy. That's one of the serious places where careful, reviewed science gets shared with the rest of the world. This wasn't a rumor or a wild guess whispered around. It was a careful, cautious, documented claim laid out for other scientists to examine. Here is what we saw. Here is what we think it means. Here is why. And what they thought it meant was breathtaking. That the most likely explanation for a clean, total, 3-hour blackout of that particular X-ray light was a planet about the size of Saturn passing in front of the source. A world in another galaxy, briefly stepping in front of a distant fire and casting its shadow all the way across 28 million light-years of empty space to fall, at last, on the patient eye of a telescope circling the Earth. I find that almost unbearably beautiful, if I'm honest. That we could be lying here, small and warm and half asleep, and somewhere in our understanding hold the shadow of a world in a galaxy we will never visit, never reach, never truly comprehend the distance to. A shadow that left its source before much of human history had even happened. That light, that missing light, that little gap of darkness, travelled for millions of years through the dark before it arrived, and we happened to be looking, and we happened to understand. But I've gotten ahead of myself, drifting off into the wonder of it, the way I tend to do. Let's come back and be careful, because being careful is part of what makes this story trustworthy. There's a question sitting right underneath everything I've just told you, and it's a fair one. If a planet in our own galaxy is already so hard to see, if we usually can't see the planet itself at all, then how could blocking a light possibly work across such a distance? Wouldn't a planet passing in front of something so far away make only the tiniest, most invisible little flicker? Wouldn't its shadow be far too faint to notice from here? And this is the clever heart of the whole thing, the part I promised would make you smile when it clicks. So let's take it slowly, because it deserves to be understood, not just believed. Think, first, about how we normally find planets around other stars, the ordinary way, inside our own galaxy. The most common method also uses shadows in a sense. It also watches for a planet passing in front of its star and blocking a little of the light. We call that a transit. The planet transits, or crosses, the face of its star, and the star dims a tiny bit. But here's the trouble. A star is enormous. A star is a huge, glowing disk of light, vast beyond imagining. And a planet, even a big one, is small compared to its star. So when a planet passes in front of a normal star, it only covers up a little sliver of that great glowing face. It blocks a fraction of a percent of the light, sometimes as much as 1% for a big planet in front of a small star, but often far less. 99% or more of the star's light keeps right on shining, straight past the planet, straight toward us. Picture it as a giant, bright window, a whole wall of glowing glass, and a single small bird flying across it. The room behind the window barely darkens at all when the bird passes. You'd have to be watching very, very closely with very sensitive instruments to even notice. And that's exactly what we do for stars in our own galaxy. We watch incredibly closely and catch that tiny, tiny dip. But now stretch that same trick across 28 million light-years to another galaxy. That tiny dip, that fraction of a percent, gets utterly, hopelessly lost. It's drowned. There's no way to catch a change that small from that far away. The signal is far too faint. The bird crossing the bright window becomes completely invisible from across an ocean. So the ordinary method, the optical transit, the visible light dip, simply cannot work at these distances. It's not a matter of building a better telescope. The signal itself is just too small to survive the journey. That door, by that method, stays shut. So how did the X-ray trick get around this? Here is the beautiful part. Here is where it all turns. The light source in the whirlpool that Chandra was watching was not a normal star. It was not a great, wide, glowing disk. It was something far stranger and far smaller. And because it was so small, everything changes. To understand what kind of object it was, I need to tell you about one of the more extreme things the universe makes. And I'll do it gently. Because there's nothing here to be afraid of. It's just physics, quiet and ancient, happening very far away. This kind of object is called an X-ray binary. Binary just means two. Two objects orbiting each other, locked together by gravity. And in an X-ray binary, one of those two objects is a normal, ordinary living star, often a big, massive one. But the other object is not a star anymore. The other object is what's left after a star has died. You see, stars don't live forever. They shine for a very long time, burning through their fuel, but eventually the fuel runs low, and the star dies. And some stars, the big ones, don't just fade away quietly. They die in a tremendous explosion, a supernova, one of the most violent events in the whole universe. And after that explosion, what's left behind is a strange, dense little corpse. Sometimes it's a neutron star, which is the crushed-down core of the dead star, packed so tightly that a spoonful of it would weigh more than a mountain. And sometimes, if the star was big enough, what's left behind is a black hole, a place where gravity has become so strong that not even light can escape it. So in an X-ray binary, you have this pairing, a living star still shining, and right beside it, the dead remnant of another star, a neutron star or a black hole. And they orbit each other close together in a slow gravitational dance. And here's what happens. The dead one, the neutron star or the black hole, has such ferocious gravity that it begins to pull material off the surface of its living companion. It steals gas, siphons it off, drags it across the space between them. And that stolen gas doesn't fall straight in. It swirls, faster and faster, spiraling inward, heating up as it goes. Until near the very center it becomes so incredibly hot that it blazes with X-rays. Not visible light, X-rays. It glows in that fierce, high-energy light that only the hottest, most violent places in the cosmos produce. And this is the crucial thing, the thing that makes the whole discovery possible. That X-ray glowing region. The hot inner zone where the stolen gas is blazing just before it disappears into the dead star is tiny. It's not a giant glowing disk like a normal star. It's a small, concentrated, ferociously bright point. In fact, that little X-ray hotspot can be roughly comparable in size to a planet itself. Small enough, at least, that a planet passing in front of it isn't like a bird crossing a giant window. It's like a hand held up in front of a candle flame. And now you can feel the whole thing turning, can't you? Because if the light source is tiny, small enough that a planet can cover it completely, then the planet doesn't block just a fraction of a percent. It blocks all of it. 100%. The light doesn't dim slightly, it goes out. Completely, it drops all the way to zero, exactly as Chandra recorded, and stays dark for the whole 3 hours the planet takes to cross, and then comes back when the planet moves on. That's the trick. That's the whole secret. A total eclipse instead of a tiny dip, and a total eclipse, a light going fully out and fully back, is a dramatic, unmistakable signal. It's not a faint flicker that gets lost across 28 million light-years. It's the light being switched completely off and completely on again. That kind of signal can survive the enormous journey. That kind of signal you can actually catch, even from another galaxy. The very smallness of the dead star's X-ray glow is what makes a planet in another galaxy visible at all. The extreme, violent nature of the source is exactly what opened the window. I love that, quietly, that it's the death of a star, the crushing of it into something tiny and fierce. That ends up making a whole new kind of discovery possible. The corpse of one star becomes the pinpoint of light against which we catch the shadow of a distant world. There's a strange gentleness in that, in how the universe sometimes hands us its secrets sideways, through its most violent doorways. So that is the object at the center of tonight's story. Not a warm, familiar sun like the one that lights our days, but an X-ray binary. A living star being slowly devoured by its dead companion, a neutron star or a black hole with a blazing hot pinpoint of X-ray light at its heart. And somewhere in that system, if the reading is right, a planet about the size of Saturn, moving in a slow, wide orbit, occasionally crossing in front of that fierce little light and blocking it entirely. And that middle part of the name, the ulls, points to just how bright and unusual this source is. These are among the most luminous X-ray sources of their kind that we know of, so bright and so extreme that they stand out, that Chandra can pick them out individually, even from another galaxy. The very brightness that let us find it is a symptom of just how violent the system is. A living star and a dead one, locked together, one feeding on the other, glowing in a light our eyes could never see, 28 million light-years away. Now, I can feel you settling deeper, and that's good. That's exactly right. So let me not rush the next part, because there's a subtlety here that I think is one of the most honest and human things about the whole story, and it deserves to be laid down softly rather than hurried. I keep saying candidate, a candidate planet, not a confirmed one. And I keep saying if it's real, and might be, and possibly. I do that on purpose, and not to be tedious. I do it because the astronomers themselves do it, and because it's the truest way to tell this story. This is a strong, careful, exciting claim. But it is not a certainty. And the reason it can't yet be a certainty is itself one of the most haunting parts of the whole thing. Think back to how planets are usually confirmed. When astronomers see a star dip just once, they don't immediately declare a planet. They wait. They watch for the dip to happen again. Because if it's really a planet in orbit, then it will come back around and cross the star again, and again on a regular schedule. Once every few days, perhaps, or once every few months. See the same dip repeat on a steady rhythm, and you can be confident. That regularity is the signature of an orbit. That's how you know. But this planet, this possible world in the whirlpool, orbits its strange dead sun on an enormously wide, slow path. It's thought to circle at a great distance from the X-ray binary, tens of times the distance between the Earth and our Sun, out where an orbit takes not days, not months, but a very long time to complete. And so, after that single 3-hour eclipse in the data, the next time this planet would pass in front of its light, the next chance we'd have to see the shadow again and confirm it, would not come for something like 70 years. 70 years. Sit with that for a moment, in the dark. We saw it cross once, and to see it cross again, to catch the second shadow that would let us say for certain. Yes, this is real, this is a world, we would have to wait roughly 70 years. Most of the people who found it will not be alive to see it. It's a discovery that reaches beyond a single human lifetime. We caught one fleeting shadow, one 3-hour blink of darkness that travelled 28 million years to reach us, and then the door quietly closed again, not to reopen within the span of almost anyone's life who's listening tonight. So they cannot simply wait and watch it happen twice. That path to certainty is closed to us, at least for now, which means they had to do something harder. They had to become detectives. They had to take that single event, that one 3-hour blackout, and ask, very carefully, what else could have caused this? Because a good scientist doesn't just leap to the most exciting answer. A good scientist tries, honestly, to rule out all the boring ones first, and only if the boring explanations fail, only then does the extraordinary one start to earn its place. And that's exactly where we'll go next, softly, in a little while. Into the careful detective work. Into the question of what else could black out an X-ray source for 3 hours, and how the team looked at the exact shape and colour of that darkness, and slowly, patiently ruled the other suspects out, one by one, until a planet was the answer left standing. There's a lovely clue hidden in the way the light disappeared, a clue about colour, about whether the darkness was even or uneven, that helped them tell the difference between a solid world and a mere passing cloud of gas. And we'll unfold that clue gently together. But for now, just rest here for a moment, in the strangeness of it all. A planet, maybe, about the size of Saturn, circling the corpse of a star in the arm of the most beautiful spiral galaxy in the sky. A world that revealed itself not by shining, but by going dark. By stepping, for 3 quiet hours, in front of a dead star's fierce little light, and casting a shadow that fell across 28 million light-years of emptiness to land. At last, on a telescope drifting high above our sleeping planet. A shadow we caught only once, and may not catch again for 70 years. Let that drift with you as we go a little deeper. There's no hurry. The planet has waited 28 million years for its light to reach us. It can wait while we take the next few steps slowly. So, let's go there together, gently. The question that's probably still sitting quietly at the back of your mind, the one that politely refuses to go away, is this one. How? How does anyone find a planet in another galaxy? How does any instrument, any telescope, any piece of machinery that human hands have built and human minds have dreamed up reach across 28 million light-years and notice something as small and dark and quiet as a single world? A planet doesn't glow on its own, after all. It doesn't announce itself. It just exists, turning slowly, cold or hot depending on its sun, carrying no sign above its door. And the answer, when you unwrap it slowly, is one of the stranger and more beautiful pieces of reasoning in all of recent astronomy. It involves a very particular kind of coincidence, not a lucky one, but a structural one, a coincidence baked into the physics of what kind of light source the planet happened to be standing in front of. So let's take it apart, piece by piece. And I'll try to make each piece sit comfortably before we move on to the next. Start here, with ordinary starlight. When astronomers hunt for planets inside our own galaxy, and they've been doing this with extraordinary patience for decades now, finding thousands of worlds in the Milky Way, the most common technique is called the transit method. You watch a star. You watch it for a very long time, sometimes years, and you wait for one of its planets to pass in front of it, as seen from our direction. When that happens, the planet gets between us and the star's light dims, just a little, for a while. Then it brightens again, once the planet has moved past. It's a little like standing at one end of a long, dark hallway, watching a lamp at the other end and waiting for someone to walk in front of it. The lamp goes slightly dimmer when they do. Not much dimmer, just a touch. But if you're measuring the light precisely enough, you can detect that dip, and from its depth and its duration, you can figure out the size of whatever was doing the walking. Now, the depth of that dip, how much the light dims, depends on how big the planet is compared to the star it's crossing in front of. A planet the size of Jupiter, crossing in front of a star, roughly like our Sun, dims the star's light by about 1%. 1 part in 100. That's actually a fairly reasonable signal to detect if the star is nearby, within our own galaxy, a few hundred or a few thousand light-years away. The Kepler Space Telescope made a career of detecting these tiny dimming events among stars in a patch of our own Milky Way. But here's the problem. 1% of a star's light, measured across 28 million light-years, is nothing. It is less than nothing, in practical terms. The star itself, from that distance, is already too faint, too small in the sky, too buried in noise and distance, and the faint collective glow of hundreds of billions of other stars in its galaxy to let you measure its brightness to 1% precision. You simply cannot do it. The signal you're looking for is, at that range, completely invisible. So planets in other galaxies should be, by any normal reckoning, permanently hidden from us. And for most of human history, and most of astronomical history, that's exactly what they were. A planet in another galaxy wasn't a thing astronomers were seriously in the business of looking for, because looking required tools that didn't exist, and physics that didn't cooperate. And then it turns out there's a loophole, a very particular, very specific loophole that only works if the planet happens to be orbiting a very particular kind of object. Not a normal star, something much stranger, something much smaller, something whose light is so concentrated, so pinched into such a tiny region that a planet's shadow can block it entirely, not dimming it by 1%, not by 10%, by 100%, switching it off completely. That's the key, that's the whole trick. And to understand why it works, you need to understand what an X-ray binary is. So let's do that now, slowly, because it's worth understanding. A normal star, a star like our Sun, is a ball of hot gas several 100,000 miles across. It's enormous. When something passes in front of it, even something as large as Jupiter, Jupiter covers only a small fraction of that enormous glowing disk. A Saturn-sized planet covers even less. The dimming is modest, the signal is small, and from far away it's undetectable. But an X-ray binary is nothing like a normal star. An X-ray binary is a system containing two objects. One is a relatively ordinary star, often a large and massive one, what astronomers would call a companion star or a donor star. And the other is something that used to be a star, but isn't anymore. Something a star becomes at the very end of its life, when it has run out of fuel and its core collapses. Either a neutron star, the crushed, city-sized remnant left behind when a massive star explodes as a supernova, or a stellar mass black hole, which is what you sometimes get when the collapse is even more dramatic. Picture the neutron star first, since it helps to have something concrete in mind. A neutron star takes what was once perhaps 10 or 20 times the mass of our Sun, a vast furnace of hydrogen and helium shining for millions of years, and packs it into a ball about 10 miles across. 10 miles. You could drive across one in the time it takes to listen to a short song. And yet it contains more mass than our Sun, squeezed to a density so extreme that a teaspoon of its material would weigh somewhere around 1 billion tons on Earth. These things are violent and strange in ways that strain the imagination. But what matters for our story is what happens when such an object sits close to another star. Because gravity doesn't become shy when a star dies. A neutron star or a black hole still pulls, and if a companion star is nearby, it pulls material off that companion, gas, plasma, the outermost layers of the donor star, and that material falls inward, spiraling down in a flat disk called an accretion disk, spinning faster and faster as it gets closer, heating up to temperatures of millions of degrees as it does. And material heated to millions of degrees doesn't glow with ordinary visible light, the kind our eyes can see or optical telescopes can detect. It glows in X-rays, hard, high-energy radiation, the same kind that passes through flesh and shows up bone in a medical scan, but far more intense. The innermost region of that accretion disk, the part closest to the neutron star or black hole, where the material is moving fastest and hottest, is the source of all that X-ray light. And here is the crucial thing. That innermost region is tiny, vanishingly small compared to a normal star. We're talking about a zone that might be a few hundred kilometers across, or a few thousand at most, depending on the system. Smaller than a moon. Smaller in some cases than a small planet. The X-ray light that blazes out of these systems is among the most energetic and concentrated light in the universe, but it comes from a source physically comparable in size to the object that might pass in front of it. Do you see where this is going? When a Saturn-sized planet drifts across the face of a normal star, it covers a tiny sliver. The star is too large, the planet's shadow too small, the dimming too modest. But when a Saturn-sized planet drifts across the face of an X-ray binary's emitting region, when that planet passes, as seen from our direction, precisely in front of that tiny superheated zone of concentrated X-ray light, the planet can cover the whole thing. All of it. The light goes from blazing to zero. Not dimmer by 1%. Off, complete darkness, where a moment before there was fierce, brilliant X-ray fire. The signal you're looking for is no longer 1%, it's 100%. The source goes from bright to completely undetectable, and 100% of a signal, even 128 million light-years away, is something you can detect. Because even from that distance, even through all that emptiness, the difference between there and completely gone is a difference your instruments can register. That's the loophole. That's the thing that makes it possible to find a planet in another galaxy, not because we got cleverer or built bigger telescopes, but because the particular system where the planet happened to be orbiting has a light source so small and so concentrated that the planet can cover it entirely. It's not a matter of improving your sensitivity by a factor of 100. It's a matter of finding, in the right galaxy, the right kind of object. And the system that produced the signal in M51, the system that Rosanne Di Stefano and her team were monitoring when they saw the X-ray light go dark, is a particularly extreme version of this. It's classified as an ultraluminous X-ray source, which astronomers abbreviate as ULX. Ultraluminous meaning exactly what it sounds like, absurdly, extraordinarily bright in X-rays, far brighter than the typical X-ray binary. These are among the most luminous single compact object systems in the known universe, shining in X-rays with a brilliance that can outshine an entire normal galaxy if you look only in that band of radiation. Why so luminous? Astronomers still debate the exact reasons in some cases, but the general picture involves matter falling onto the compact object at a very high rate, a lot of material being stripped from the companion star and falling inward, releasing huge amounts of energy as it does. The precise mechanics can get complicated, and there's still research being done into just how these systems manage to shine so brightly, but for our purposes what matters is the effect. An ultraluminous X-ray source is, in X-ray terms, extraordinarily bright, and its emitting region is still small. That combination makes it monitorable even from across the gap between galaxies. Chandra, the NASA X-ray Observatory that was watching when the light went out, was launched in 1999. It was sent into a highly elliptical orbit that takes it more than a third of the way to the Moon at its farthest point, lifting it above Earth's atmosphere so that X-rays from distant sources can reach its detectors without being blocked by the air that protects our surface from exactly this kind of radiation. Chandra's mirrors, curved nested cylinders, polished to extraordinary smoothness, graze incoming X-ray photons at very shallow angles and redirect them to a focus. It has the sharpest X-ray vision of any telescope ever built, able to resolve individual X-ray sources in nearby galaxies and track their brightness over time with remarkable precision. And so, over the years, Chandra had gathered observations of M51, the Whirlpool Galaxy, watching the X-ray sources scattered across its disk. These binaries and their companions, these tiny fierce systems of dead stars consuming living ones, distributed here and there throughout the galaxy's 100,000 light-year span, each one a point of hard radiation in Chandra's field. The team studied the archives of these observations, scanning for things that had changed, for sources that had done something unusual, for a light that had, at some point in the record, gone out. And they found it. In the archive data, the ultraluminous X-ray source known as M51 ULS1 had, at some point during one of Chandra's observation windows, gone completely dark. Not flickered, not dimmed, gone. The X-ray flux dropped to what the data described as essentially undetectable levels. And then, about 3 hours later, it came back. Smoothly, symmetrically, the brightness returning in a way that mirrored how it had faded, until the source was shining again, as though nothing had happened. 3 hours of silence. 3 hours during which something had placed itself, from Chandra's perspective, directly between us and the fierce bright pinpoint of that dying system, blocking every X-ray photon that might otherwise have made the journey. And then, as quietly as it had arrived, whatever it was moved on. Now the team couldn't simply declare victory. A total X-ray blackout is dramatic, but it isn't automatically a planet. The universe has other ways of making X-ray sources go quiet, and a rigorous scientist, as I mentioned a little while ago, is obliged to examine all the less extraordinary explanations before reaching for the extraordinary one. So what else could have caused this? One obvious candidate is a passing cloud. The space between stars in a galaxy isn't perfectly empty. It's threaded with gas and dust, and sometimes a cloud of this material drifts across the line of sight to a bright source. The cloud absorbs some of the radiation trying to pass through it. Could that explain the dip? Here's where the clue I mentioned earlier, the clue about color, becomes important. Gently, carefully, let me explain what that means. X-rays, like visible light, come in different energies. Just as visible light has colors, red at the low energy end, blue and violet at the high energy end, X-rays have a range of energies, and we sometimes think of the lower energy X-rays as softer and the higher energy ones as harder, as in more penetrating. When radiation passes through a cloud of gas or dust, it doesn't pass through uniformly. Lower energy photons, the softer X-rays, are absorbed more readily by the gas than higher energy ones. The cloud acts as a filter that preferentially soaks up some colors and lets others through. This means that if a gas cloud drifts in front of an X-ray source and dims it, the dimming is not the same at all energies. The spectrum of the source changes. The X-ray color shifts as the softer photons are stripped away. Astronomers call this an energy-dependent absorption signature, and it's a recognizable fingerprint of intervening gas. The eclipse in the M51 data showed no such signature. The darkening was what astronomers call achromatic, grey, if you want a color language analogy, even though we're talking about X-rays. The source didn't just dim, it was blocked equally across the energy range. Soft X-rays vanished. Hard X-rays vanished. Everything vanished together, in proportion, with no preferential filtering of any particular energy band. That's exactly what you'd expect if a solid, opaque object, something that simply covered the source and blocked everything, had passed in front of it, rather than a wispy, semi-transparent cloud that would let the harder photons through while catching the softer ones. The shape of the light curve also mattered. The way the brightness fell at the beginning and rose at the end. That symmetric profile, fading in and then recovering in a matched curve, was consistent with an object of planetary scale moving smoothly across the compact emitting region. Not the irregular, lumpy variations you might expect from a cloud drifting and shredding under gravitational forces. A clean transit, a planet-shaped shadow. Taken together, the total extinction, the achromatic quality, the symmetric light curve, the 3-hour duration, the evidence pointed away from a gas cloud and toward something solid. Something that didn't absorb or filter, but simply blocked. Something opaque and coherent. Something, in short, the size of a planet. The team also considered whether the source itself might simply have been doing something unusual. Sometimes X-ray binaries vary in brightness naturally, flaring up and quieting down as the accretion process shifts. But the behavior didn't fit the known patterns of natural variability in these systems, which tend to be noisier and less symmetric. A natural brightness dip would typically not produce such a clean, smooth, symmetric, total extinction. The data didn't look like a coughing X-ray binary, it looked like something passing in front of one. And so, ruling out the gas cloud by its achromatic fingerprint, ruling out natural variability by the shape of the dip, the team was left with the most consistent explanation. a solid body, roughly the size of Saturn, had crossed in front of the X-ray-emitting region of M51 Ulls-1, a planet-sized transit, the first ever observed outside the Milky Way. The team used data from NASA's Chandra X-ray Observatory as their primary dataset, but they also looked to a second instrument for additional context. The European Space Agency operates its own X-ray space telescope called X-ray-emitting, which has been collecting X-ray data since it launched in 1999, the same year as Chandra. X-ray-emitting has different strengths from Chandra. It collects more X-ray photons per unit time, making it especially useful for studying the brightness and spectral properties of sources in detail. The team considered X-ray-emitting data as part of the broader picture, lending further context to the observations of the M51 system. There's something I want to sit with for a moment before we move on, because I think it's worth appreciating slowly. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. So, where were we? The data, the light that went out. The Chandra observations of M51 weren't collected specifically to look for planets. They were collected over years as part of a range of scientific programs, and they happened to contain this signal buried in the archive, waiting to be found. Rosanne Di Stefano and her colleagues developed a method for searching through archives of X-ray data from nearby galaxies, looking for just this kind of event, a transient, total eclipse of a compact X-ray source. And in M51, they found it. That word, transient, is important. It means something that happens once, briefly, and isn't repeating in the dataset. This transit was a single event in the Chandra record, one occurrence, which is part of why, despite everything the data shows, the scientific community holds this result carefully, with admiration and also with an honest caution. Because here's the difficulty. One transit isn't enough to confirm a planet. When astronomers confirm planets inside the Milky Way using the transit method, they typically require at least 3 observed transits, 3 separate occasions when the planet passed in front of the star and the brightness dipped in a consistent, repeating way. That repetition tells you the object is in a regular orbit. It tells you the first transit wasn't a random coincidence or an instrumental artifact. 3 transits means you've measured the orbital period, which tells you how far the planet is from its star, which locks in the whole physical picture. But M51 Ulls-1b, if it's real, orbits at a vast distance from its host. The team estimates it orbits at tens of astronomical units from the compact object at the center of that binary system. An astronomical unit, just to keep that scale in mind, is the average distance between the Earth and the Sun, about 93 million miles. Saturn orbits our Sun at roughly 9.5 astronomical units. This candidate planet is thought to orbit at a comparable distance, or perhaps even farther out, which means its year, the time it takes to complete one full orbit, might be decades long. If the orbit is that long, the planet would cross in front of the X-ray source, as seen from our direction, very rarely. Perhaps once every several decades. And the window during which that transit is visible, from our particular vantage point, might be only a few hours each time it occurs. The team calculated that the next transit wouldn't be expected for approximately 70 years. 70 years. Think about what that means for the human ambition to confirm this discovery. The astronomers who published this result in 2021 would need to live well into their 90s or beyond to have any hope of seeing a second transit, even if Chandra or its successors are still operating in 2091 and are pointed at the right source at exactly the right moment. And there's no guarantee the geometry will still be favorable from Earth's perspective by then. Orbital configurations shift. The viewing angle that let us catch this transit in the first place may not repeat on the same geometry. So the discovery sits in a kind of beautiful and frustrating suspension. The evidence for a planet is real and careful and honestly presented. The mechanism by which it would have been detected is physically sound. The alternative explanations were examined and found to fit the data less well. And yet, because science is rigorous and honest, because a single event, no matter how persuasive, cannot be held to the same standard as a repeating measurement, M51 ULS 1b remains a candidate. The team described it as a planet candidate, and the community has largely received it that way, as a fascinating, probably real, but not formally confirmed discovery. There's something almost poetic about that. A world that reveals itself once, with a 3-hour shadow falling across 28 million light-years of empty space, and then retreats into silence for the length of a human lifetime. A discovery that can't be taken back and can't quite be completed. A door opened, a glimpse offered, and then the door drifting shut, slowly, as the planet continues its long, dark orbit. But here's what we also know about this world, or at least what we can infer about it from what the data offers. And spending a few moments with those inferences, I think reveals something quietly astonishing about where this planet lives. Its size, based on how completely it blocked the X-ray source and how the light curve shaped itself over those 3 hours, is estimated to be roughly that of Saturn. Saturn, in our own solar system, is the ringed giant, the second largest planet. A world of golden bands and spectacular rings that has delighted astronomers since telescopes were invented. It's about 9 times the diameter of Earth, a gas giant made mostly of hydrogen and helium with a small rocky or metallic core at its heart. So we're talking about a candidate planet that is substantial, not a small rocky world like ours, but something large and gaseous. It orbits its host at a distance of tens of astronomical units, which means, in the imagination at least, it drifts at a considerable remove from the blazing violence at the center of its system. Far enough, perhaps, to have been shielded from some of the worst of it. Although shielded is a relative term when your sun is a neutron star or black hole. And that dead sun at the center, is perhaps the strangest and most haunting detail about this candidate world. Because to orbit an X-ray binary is to orbit the aftermath of a catastrophe. What we mean when we say neutron star or black hole is that whatever was once a normal star, a star that lived and burned and shone for millions of years before the planet's orbit was established, is no longer there. It exploded. At some point in this system's past, the more massive of the 2 original stars ran out of fuel. The nuclear fire that had held it up against gravity for its entire life went out, and in a fraction of a second the core collapsed, triggering a supernova explosion that briefly outshone the entire galaxy around it. What was left was either a neutron star, that impossibly dense city-sized ball of compressed matter, or, if the star was massive enough, a black hole from which nothing, not even light, can escape. If this planet is real, it has survived all of that. It formed, perhaps around the normal stars that existed before, and then it watched, if we can grant it the luxury of a metaphor. One of its suns die in the most violent way the universe knows how to kill a star. And still it orbits. Or perhaps it formed later from material thrown outward by the supernova itself, or captured from surrounding space in the aftermath. The details of how a planet survives or forms in a system like this are genuinely uncertain. But the fact that we're entertaining the possibility at all tells you something about how resilient, or at least how various, the conditions under which planets can exist appear to be. The companion star, the surviving ordinary star, the donor whose material is being stripped away by the compact object, is thought to be a large, massive star, probably what astronomers would classify as something like a blue supergiant, hot, luminous, enormous. It's the engine that feeds the accretion disk with its gas, the source of the material that falls inward and heats up and produces all those blazing X-rays. This star is also, in astronomical terms, not long for the world. Massive stars burn fast and die young, and this one is slowly being consumed from without, its outer layers peeling away into the maw of the compact object beside it. The system the candidate planet orbits is, in a real sense, a system in the process of destroying itself. And yet, drifting somewhere in the dark at tens of astronomical units from this unfolding catastrophe. Orbiting with the patience of something that has kept its path for millions or billions of years, something like a Saturn-sized world may simply be continuing to turn. There's no rush. None of this is going anywhere soon. The planet will still be there, quietly orbiting, while you drift towards sleep. So, let me see if I can gather what we've built together so far, and hold it gently before we move on. We started with the fact that finding a planet 28 million light-years away should be, by the standards of ordinary astronomy, impossible. The signal an ordinary transit produces, a planet dimming a star's visible light by a fraction of a percent, is too small, too faint, too buried in noise and distance to detect across the span of another galaxy. What changed everything was the presence of the right kind of light source. An X-ray binary, a compact object, a neutron star or black hole, surrounded by a tiny, searingly hot region that blazes in X-rays but is physically no larger than a planet itself. A source that a Saturn-sized world could block entirely. Not dim by 1%, but extinguish by 100. The Chandra X-ray Observatory caught that extinction. 3 hours of darkness where there had been X-ray fire. A symmetric, clean, smooth dip that looked like a transit. And crucially, a dip that was achromatic, identical at all X-ray energies, no energy-dependent absorption, no sign that a gas cloud had filtered some wavelengths while letting others through. The darkness was even. The darkness was total. The darkness was the signature of something solid. The candidate was designated M51 ULS 1b. The system sits in the Whirlpool Galaxy, Messier 51, about 28 million light-years from where you're lying right now. The work was led by Rosanne Di Stefano of the Harvard-Smithsonian Center for Astrophysics and published in Nature Astronomy in September 2021. The source is an ultraluminous X-ray source, among the most energetically violent compact object systems in the known universe. The planet, if real, is roughly Saturn-sized, orbiting at a great distance from its host, with an orbital period that might span decades. The next chance to confirm a second transit won't come for approximately 70 years. That's what we have. That's the mechanism, laid out as honestly and as carefully as the team who found it laid it out themselves. But there's a whole other layer to this story that we haven't touched yet. Because the Whirlpool Galaxy, Messier 51, NGC 5194, the textbook example of the grand design spiral, the most photographed galaxy in the sky for generations of amateur and professional astronomers alike, is not just the backdrop to this discovery, it's part of the story. And the reason it exists the way it does, so perfectly, so elegantly, with those clean, sweeping arms that make it the most recognizable face in the deep sky, is a reason that connects, in a surprising way, to the very systems inside it that let this planet be found at all. The Whirlpool Galaxy is beautiful, and the reason it's beautiful is violent. But that's where we'll drift next, slowly, into the history of the whirlpool itself, a collision in progress that has been sculpting its elegance for hundreds of millions of years. Into the companion galaxy, NGC 5195, that perches at the tip of one of those spiral arms, like something placed there deliberately, and what its gravity has been doing to the space around it. Into the connection between that gravitational drama and the extreme stars, the blazing, violent, compact systems that the collision has helped create. And into the question of what it means for the planet, for the galaxy, for the strangeness of finding a world this way, that beauty and violence turn out to be, in this case, the same thing wearing different faces. So for now, let your breathing slow. Let the number 28 million settle, as a number doesn't need to be fully grasped to be felt. Let the image of a Saturn-sized world, drifting in darkness, orbiting the grave of a star, rest somewhere comfortable at the edge of thought. There's more to tell, and we have all the time in the world to tell it. So let's think about the planet itself for a moment. Not the method, not the telescope, not the mathematics of why an X-ray source works when ordinary starlight doesn't. Just the object, the world, the thing itself. Because there's something quietly extraordinary about sitting with what the data actually suggests, before we ask whether it's confirmed or not. Before we weigh all the careful caveats. There is a shape in the data. And the shape is a planet. It's roughly the size of Saturn. Let that land gently, if you can. Saturn, that pale gold-ringed world you've probably seen in a photograph at some point, the one that looks almost too beautiful to be real, too perfectly round and ringed and serene to be anything other than a painting. If you've ever looked at Saturn through even a modest backyard telescope, you'll know the strange feeling it gives, a flicker of disbelief that a planet can look like that. That nature just makes things that beautiful for no apparent reason. Saturn is about 9 times the width of Earth across the equator. Its rings, if you laid them flat, would just barely fit in the space between Earth and the Moon. It's enormous by any human reckoning, and yet modest by the standards of the gas giants. Not a Jupiter, not a behemoth. Something quieter, something ringed and golden and ancient. And whatever is moving in front of that X-ray source in the Whirlpool Galaxy, 28 million light-years away, appears to be roughly that size. The data can't give us rings. It can't give us color or atmosphere or any of the features we associate with a specific world. What it gives is a size estimate, an inference drawn from the duration of the eclipse, the crossing speed, the geometry of the system, and the estimate comes back as approximately Saturn-sized. A body large enough to blot out the X-ray source completely, but not so large it would have taken longer to cross, not so small the numbers stop working. Something in the Saturn range. A world you could, at least in imagination, picture, and then you picture where it is, what it orbits, and the image changes. Because this is not a peaceful system. This world, if it exists, and the data suggests it might, is not circling a yellow star on a warm spring afternoon somewhere. It's not bathing in gentle light at a comfortable distance. It's out in the darkness, far out, at a distance from its host, measured in tens of astronomical units. To give that some shape, 1 astronomical unit is the distance from the Earth to the Sun. Roughly 93 million miles, if miles mean anything to you at this scale. And this planet is thought to orbit at a distance comparable to or even farther than Saturn sits from our own Sun, which is about 9.5 astronomical units, so we're talking tens of AU. Deep space, by any solar system standard, a very long orbit around a very unusual center of gravity. Which means the year there, if you could walk that world's surface and count the time it takes to complete one trip around its host, might be decades long. Decades, not a year in the human sense. Not 12 months and a birthday and the seasonal turning of the calendar, but something like 10 years, or 20, or more. A long, slow drift through a wide orbit. And in all that time, in all those decades, the planet would be moving against a sky that is nothing like our sky, around a source of energy that is nothing like our sun. Because the thing at the center of this system isn't a star in any normal sense. Not anymore. Let's talk about that. Let's move slowly through what the object at the center of this system actually is, because it matters, not just as a fact, but as a feeling. It changes what it means to imagine this world. The thing this planet orbits is what astronomers call a compact object. Specifically, the system it's part of, the ultraluminous X-ray source designated M51 ULS-1, is what's known as an X-ray binary. We touched on this a little when we were talking about the detection method. But now let's really sit with what that means. An X-ray binary is a pair of objects caught in a kind of slow, violent embrace. On one side of the pair, there's a normal star, massive, bright, burning, often what astronomers call a blue supergiant, a star many times heavier than our Sun, running hot and fast and brilliant, pouring out enormous amounts of radiation. These are the kind of stars that don't last long by cosmic standards. They burn bright, and they burn quick, and they end badly. Millions of years, not billions. A mayfly by stellar timekeeping. On the other side of the pair, the compact object is what's left after another star already ended badly. Because at some point in the past, this system had 2 stars, 2 massive, blue, brilliant objects orbiting each other, and at some point, one of them reached the end of its life. Stars like this don't fade gently. They don't dim gradually and cool into retirement. They explode. In a fraction of a second, the core of the star collapses, squeezed by gravity so intensely that the laws of physics we use for everyday objects simply break down, and the outer layers of the star are blasted outward in a catastrophic explosion called a supernova. The kind of explosion that, for a brief window, can outshine an entire galaxy, something so violent it strains the imagination to take seriously. And what's left behind, in the center, after all that fury? Either a neutron star or a black hole. Those are the 2 candidates for what sits at the heart of this system, and the data doesn't yet tell us which. A neutron star is itself already one of the strangest objects in the known universe, a mass roughly 1.5 times the Sun's, compressed into a sphere about the width of a city, maybe 10 or 12 miles across. All that mass, all that gravity, all that density, packed into something you could theoretically drive across in 20 minutes if you weren't worried about what happened when you got there. Neutron stars are so dense that a teaspoon of their material would weigh hundreds of millions of tons. They spin, some of them, hundreds of times per second. They have magnetic fields so powerful that if you were 1,000 miles away, still impossibly far by human thinking, but relatively close by astrophysics, the field would be strong enough to destroy atomic structure. Or it might be a black hole. A stellar mass black hole formed from the complete collapse of the dead star, a region where gravity curves space-time so intensely that nothing, not even light, escapes from within a certain boundary. Either of those is at the center of this system, and it's pulling matter off the companion star, the massive blue supergent still burning nearby, in a continuous stream. The gravity of the compact object draws in gas from the companion's outer layers, and that gas doesn't fall straight in. It spirals, forming a disk around the compact object, an accretion disk, a flat whirlpool of superheated matter swirling faster and faster as it falls inward, heated by friction and compression to temperatures of millions of degrees. So hot it glows, not in visible light, not in the warm yellow or red we associate with ordinary stars, but in X-rays. Hard radiation, high energy, the kind of light that passes right through you without asking permission. That disk, specifically the innermost region of that disk, the part closest to the compact object, where the temperatures are highest and the radiation most intense, is the X-ray source. And that region is small, extraordinarily small, not star-sized, not even close to star-sized, something more like the size of a large planet or a small planetary system. Tens or hundreds of miles across, maybe, a point of light so tiny that, as we talked about, a Saturn-sized object can block it completely. That is what this candidate planet orbits. The aftermath of a supernova, a neutron star or a black hole eating its companion, a disk of superheated material glowing in X-rays, a system that generates more energy in 1 second than our sun does in thousands of years. It's classified as an ultraluminous X-ray source, which means it's among the most brilliantly luminous compact object systems known to exist. Extraordinary energy, extraordinary violence, and far enough away at tens of astronomical units that the planet, if it's there, traces its slow decades-long orbit around all of it. What does the sky look like from that world? You can't know, of course. Not really. But you can imagine. At tens of AU, the compact object and its companion star would appear as a brilliant, tiny point. Not the warm, broad disk of a sun, but a concentrated, fierce, blazing source. High-energy light pouring out in all directions, and that planet, if it has a surface, or an atmosphere, or anything to receive and respond to that light, would be receiving something unlike anything in our own solar system. Not warm, nurturing starlight, but hard radiation. X-rays and ultraviolet, and the full, fierce spectrum of a dying system's death glow. And around it, the darkness. And overhead, presumably, if there's something overhead to look up into, the Whirlpool Galaxy itself spreading in all directions. Because the planet is inside M51, not looking at it from outside. The stars of M51 would be the sky. The spiral arms, if you could perceive them at that scale, would be the fabric of the night, dense with suns. It's a strange thought. A planet inside a spiral galaxy different from our own, looking out at a universe we would also recognize, but from a vantage point 28 million light-years away from here. Let that go gently. No need to hold it firmly. Just let the image float, loose and quiet, at the edge of whatever thoughts you're still keeping. And let's talk about the galaxy itself. because we've been speaking of it as a setting, as a backdrop, as the distant stage on which this detection played out. But the Whirlpool Galaxy has its own story, and it's a long one, and it's a beautiful one, and it begins long before any of us were here to notice it. Let me take you back to 1773. A summer night, somewhere in Europe, and a French astronomer named Charles Messier is doing what he does most clear evenings, hunting the sky for comets. Messier is one of the great comet hunters of his era, and he is methodical, patient, careful. He keeps a catalogue, a famous catalogue, the one that still bears his name, not of wonders exactly, but of things that might fool a comet hunter. Fuzzy patches of light in the sky that could, at a glance, be mistaken for a comet but aren't. Clusters of stars, clouds of gas, distant glows of uncertain nature. He catalogues them so he doesn't waste time investigating them again. And in 1773, into that catalogue of not comets, he places an entry. Messier 51. A faint smudge of light in the constellation Canes Venatici, the hunting dogs, a small, somewhat obscure constellation that sits near the handle of the Big Dipper in that region of sky between the Big Dipper and the star Arcturus, on autumn evenings in the northern hemisphere. The smudge is unremarkable to Messier's eye. Not a comet, a blur, a glow, a soft nebulosity. He notes it and moves on. He doesn't know what it is. Nobody does in 1773. The tools and the concepts needed to understand what he's looking at don't yet exist. The very idea that there are galaxies outside our own, that the universe contains billions of cities of stars, each containing billions of stars, spread across distances so vast they dwarf the imagination, is decades away from becoming accepted science. In 1773, the Milky Way is essentially the universe, and Messier 51 is a curiosity without a category. It stays that way for decades. Just a blur. Then comes the spring of 1845, and the story changes. In the west of Ireland, in County Offaly, there is an estate called Birr Castle. And at Birr Castle, a man named William Parsons, the third Earl of Ross, has spent years building something extraordinary. A telescope. But not just any telescope. Something that, in 1845, is the largest telescope in the world, a 6-foot aperture reflector, its massive metal mirror cast and polished to extraordinary precision, mounted on stone walls and moved by an elaborate system of chains and counterweights. The tube alone is 58 feet long. People called it the Leviathan of Parsonstown, and in 1845 Lord Rosse points the Leviathan at Messier 51. What he sees is not a blur. What he sees for the first time in human history is a spiral. He sketches it by hand, the way all astronomical observations were recorded before photography, patiently, carefully, by eye at the eyepiece, and the sketch shows unmistakably what he's looking at. Not a cloud, not a cluster, a form, a pattern. Arms sweeping out from a bright centre in graceful curves, winding around and away, with something else nearby, a companion, a secondary glow perched at the end of one of the arms. He doesn't know what it is either. The word galaxy isn't yet being used the way we use it now. He calls it a nebula, the catch-all term for any deep sky smudge, and notes its spiral structure, which is unlike anything previously observed. But the shape is there, in the sketch, undeniable. Messier 51 is the first galaxy in which spiral structure was ever identified by a human eye and recorded. The very first. And the structure that Lord Rosse saw in 1845, the form that made his sketch so remarkable, the clean, sweeping arms that make the Whirlpool Galaxy the most recognizable face in the deep sky, that structure has a reason. And the reason is the thing perched at the end of one of the arms that he noticed in that same sketch. The companion, the small glow beside the main glow. NGC 5195. Let's talk about NGC 5195 for a moment, because it's important and it's worth understanding what it is and what it's doing. NGC 5195 is a smaller galaxy. Not tiny, but smaller than M51, a compact, somewhat irregular form that sits at the tip of one of M51's two great spiral arms, as if placed there deliberately, as if the Whirlpool has a jewel at the end of its arm, or perhaps a fish on a hook, or perhaps, and this is closer to the truth, as if the Whirlpool has caught something and hasn't quite let go yet. The two galaxies are gravitationally bound, entangled, falling toward each other and around each other in a slow, vast gravitational dance that has been going on for hundreds of millions of years. And at some point in the deep past, models suggest hundreds of millions of years ago. NGC 5195 made a passage through or near M51's disk, not a gentle pass, a plunge. The smaller galaxy moving through the flat plane of the larger one, its gravity dragging at the stars and gas and dark matter around it, pulling and distorting and compressing. And here's the thing about that passage, about what it did. When a galaxy, or anything massive, moves through the disk of a spiral galaxy, the gravity of that passing object does something to the density waves that already exist in the disk. Spiral galaxies have density waves, somewhat like sound waves, moving through the disk. Regions of slightly higher density that rotate around the center, and as clouds of gas and stars pass through those denser regions, the compression triggers star formation. New stars born from the squeezed gas. What NGC 5195's passage did, and keeps doing, because the interaction is ongoing, the two galaxies still entangled, is amplify those density waves, sharpen them. The gravitational pull of the companion enhances the wave pattern, pushes the spiral arms into greater relief, makes the structure more pronounced, cleaner, more dramatic. The arms you see in a photograph of M51, the gorgeous, textbook-perfect spiral arms that make it one of the most reproduced astronomical images in history, are that clean because NGC 5195 keeps sharpening them. The most beautiful galaxy in the sky is beautiful because it's being disrupted. The elegance is a symptom of the violence. The sweeping arms are density waves amplified by gravitational intrusion. The star formation happening all along those arms, the bright young blue stars lighting up the spiral from inside, is compressed gas, compressed by the same disturbance. Beauty and violence, wearing the same face. Over cosmic time, billions of years from now, far beyond anything that touches human history or human scale. What is now a passage and an entanglement will become a merger. The two galaxies will fold into each other. NGC 5195 will not escape the Whirlpool, it will become part of it. A slow consumption, gradual and inevitable, a minor merger that will eventually make M51 slightly larger, slightly heavier, the smaller galaxy absorbed into the structure of the larger one. Astronomers sometimes call this kind of thing galactic cannibalism. The large eats the small, not in a moment but over eons. But we are in the middle of that process right now. Or rather, we're watching the light from the middle of that process, as it was 28 million years ago, because that's how far away the Whirlpool is, and light takes time. The light from M51 that your eyes could see on a very dark night with good binoculars, or that the Hubble Space Telescope has captured in such extraordinary detail, left that galaxy before any of what we recognize as human civilization existed. Before the pyramids, before writing, before cities, before really anything we'd call history. And in that same galaxy, at that same moment in the past, a planet was either casting a shadow across an X-ray source or something else was. And Chandra, pointed at that galaxy's light from 28 million light-years away, recorded what happened. Recorded the 3-hour blackout. Recorded the grey eclipse, the achromatic dimming, the symmetric dip, and recovery. The detection and the galaxy's beauty are in the end part of the same story. The companion galaxy's gravitational intrusion doesn't just sculpt the arms, it compresses gas, drives star formation, and in a galaxy filled with active star formation, the rate at which massive stars are born is high. Massive stars burn bright and fast and end badly. They leave behind compact objects, neutron stars, black holes, and some of those compact objects orbiting other stars become X-ray binaries, and some of those X-ray binaries become ultraluminous X-ray sources, brilliant enough to be seen individually from 28 million light-years away. The Whirlpool has more than its share of ultraluminous X-ray sources, more than a quieter, undisturbed galaxy might have. The violence of the interaction helps produce the extreme stellar systems, and one of those extreme stellar systems, one neutron star or black hole pulling matter off a massive companion, generating X-rays in its tiny, hot accretion zone, turned out to be the one in front of which a planet moved. The prettiest galaxy and the most extreme planet, connected not by coincidence but by causation. The violence that made M51 beautiful is the same violence that built the kind of system where a planet could be caught casting a shadow at 28 million light-years. It's worth sitting with that for a moment. The way one thread runs through all of it. Charles Messier recording a smudge in 1773. Lord Rosse seeing a spiral in 1845 and drawing it by hand in the Irish night. A smaller galaxy plunging through a larger one, hundreds of millions of years ago, sharpening the arms, compressing the gas, igniting waves of star formation, seeding the population of massive blue stars that would burn fast and leave behind compact objects. One of those compact objects falling into orbit with a surviving companion. Matter spiraling in. X-rays blazing out from a region the size of a city. A Saturn-sized world moving in front of it for 3 hours. And Chandra, a telescope launched in 1999, pointed across an almost incomprehensible distance, recording the shadow. It's a long chain, a very long chain, spanning hundreds of millions of years of galactic history, and one autumn week in 2021, when Rosanne Di Stefano and her colleagues at the Harvard-Smithsonian Center for Astrophysics looked at the light curve and saw what the data was suggesting. You don't have to hold all of that at once, just feel the direction of it. The sense that discovery doesn't happen in isolation. It happens at the end of a chain you can trace backward, event by event, each one turning out to be necessary for the next. The Whirlpool Galaxy. Messier 51. The most photogenic spiral in the sky. A collision in progress, a merger in slow motion, a canvas of star-forming violence dressed up as elegance. And somewhere inside it, if the data is right, a world drifting in darkness at the edge of a dead star's light. Let's talk about what kind of place that might be to drift. Not because we can know, we can't. The data doesn't reach that far. But thinking about it, carefully, gently, with appropriate humility, helps make the distance real. Helps give the number some texture. The planet is far from its host. Tens of astronomical units. At that distance, even the extraordinary energy output of an X-ray binary would be spread thin across the intervening space. Energy follows an inverse square law, which is a way of saying that doubling the distance reduces the intensity to a quarter, tripling the distance reduces it to a ninth, and so on. At tens of AU, the radiation reaching the planet is diluted by distance. Still not nothing, X-ray binaries are enormously luminous, but not the blazing nearby inferno you might imagine. What the planet would receive is hard radiation, not the warmth of a yellow star. X-rays and the harder ultraviolet end of the spectrum, the kind of radiation that our atmosphere here on Earth filters out, that astronauts on long space missions have to think carefully about. For a rocky planet, it would likely strip away any light atmosphere over time. For a gas giant, something Saturn-sized, with deep gravity and vast atmospheric reserves, the story might be different. A massive enough atmosphere might hold together against even that. Might. But the question of habitability, whether anything could live there, whether the conditions allow for the chemistry of life as we understand it, is one the data doesn't invite us to answer. Not because the answer is obviously no, but because the question is simply beyond what we can responsibly say from a 3-hour X-ray dip recorded by Chandra at 28 million light-years. What we can say is that the system is extreme by any measure. A violent heart, a hard radiation field, a long, wide, slow orbit through the dark. And one more thing, this world has already survived something enormous. Because if the planet is there now, orbiting the compact object, the neutron star or black hole, it was there before the supernova too, or formed afterward from the debris the explosion left behind. Both are possible, and astronomers have thought about both scenarios in other contexts. Some planets are ancient, formed early in a system's history and surviving the later death of a star. Others may form from the material expelled in a stellar explosion, born not from a protoplanetary disk around a living star, but from the chaos of a stellar death. These are called secundary planets or post-supernova planets, and a few examples have been found in our own galaxy in similarly extreme environments. Either way, whether this world predates the supernova or was born from it, it has persisted. Through the explosion, through the aftermath, through however many millions of years, the compact object has been pulling matter from its companion. It has continued in its orbit, following its decades-long path, unaware of any significance we might attach to it. Worlds don't know they're being looked at. They don't know they're extraordinary. They don't know that 28 million light-years away, a species on a pale blue dot in a quiet outer arm of a different galaxy built a telescope, launched it into orbit, aimed it at the right source at the right moment, and caught the shadow they cast in a 3-hour window of darkness. They just keep moving, patient and indifferent in the dark. There is something in that thought that is either lonely or peaceful, depending on how you're feeling right now. The planet doesn't need us to notice it. It was there before Charles Messier wrote his catalogue entry in 1773. It was there when Lord Rosse sketched the spiral arms by eye through the Leviathan. It was there when the light we detected left its galaxy 28 million years ago, before anything walking on this planet looked up and wondered about the stars. And it will be there, probably, long after the current generation of telescopes is replaced by the next and the next and the next. Our observation of it lasts 3 hours. Its orbit takes decades. Its galaxy's collision has been in progress for hundreds of millions of years. Scale is a strange thing to carry to sleep, but there's something restful in it too. The way the universe keeps doing what it does without requiring our attention. The way stars form and die and collapse and attract and repel and pulse and rotate on timescales that have nothing to do with human urgency. You can let go of your sense that things need to be resolved quickly or understood completely when you're thinking at this scale. Nothing at this scale resolves quickly. Nothing is fully understood. And that's fine. So let's stay with the whirlpool a little longer. Let's let it fill the mind the way it fills an image, that gorgeous, improbable face on spiral, looking back at us from Cain's Venatici, the hunting dogs, near the handle of the Big Dipper. On a clear autumn night in the northern hemisphere, it's there. You can't see it with the naked eye, but you can find it with binoculars if you know where to look. A faint smudge, a soft glow, just as Messier saw it, just as it appeared to every human eye before Lord Rosse gave them the context to understand what they were actually looking at. The Big Dipper's handle sweeps down and east, and from the second star at the handle's end, a star called Messier. You can draw a mental line south toward a bright orange star, Arcturus, and about halfway along that line, slightly west, is the area of sky where M51 lives. Not visible as a shape, not visible as a spiral, just a hint of light if you know where to look. But it's there. And it's enormous. And it's in motion. And inside it, somewhere, a Saturn-sized world is moving through its decades-long year around a burning, collapsed, violent point of gravity. The mind can rest on that. You don't have to do anything with it. You don't have to solve it or sort it or come to any conclusion about what it means. It is simply true, or probably true, or at least possibly true, in ways the data strongly suggest. And the truth of it is enough. A planet, in another galaxy, found by its shadow. There's one more piece of this story that we haven't yet fully told, and it's the piece that brings the discovery back to something almost personal, something about what it means to find something this way, at this distance, with this much uncertainty, and choose to publish it anyway. To say, we can't confirm it. We may never confirm it. But here is what we saw, and here is what it suggests, and here is the honest accounting of why we believe, and why we doubt, and what would need to happen next. That's where we're going next, into the question of the 70 years, and what it means to make a discovery you cannot verify, and what the data still holds that we haven't yet examined. But that comes in a moment. For now, settle back into wherever you are. Feel the weight of where you're resting. The ordinary strangeness of a warm room on a planet in a quiet galaxy, where someone built a telescope that can catch a shadow from 28 million light-years away. That really happened. In September 2021, Rosanne Di Stefano and her colleagues looked at that data and said, something passed in front of that source. Something roughly the size of Saturn. Something solid. Something real. And the Whirlpool Galaxy, with all its history, all the ancient violence of its collision with NGC 5195, all the star formation and stellar death and compact object creation that collision seeded over hundreds of millions of years, all the way back to a comet hunter's notation in 1773, and a nobleman in County Offaly drawing spirals by hand through the biggest telescope in the world. The Whirlpool Galaxy, all of it, was the stage on which that happened. A pretty galaxy. A violent one. And, possibly, a galaxy that contains a world. So let's talk about the spiral. Because you've probably seen it. Even if you've never looked at a telescope, even if astronomy has never been a particular interest of yours. There's a good chance you've seen a photograph of the Whirlpool Galaxy at some point in your life and not even known what you were looking at. Maybe it was on the cover of a book, or on a poster on someone's wall, or in one of those slow documentary sequences where they pan across a deep field image and the music swells. There it is, this perfect, almost geometrically pristine spiral. Two great arms curling outward like a watch spring, unwinding in slow motion, defined and clean and laced with blue-white clusters of hot young stars, framed against the dark, and at the tip of one arm, seemingly resting there, like a charm on a bracelet, a smaller, fuzzier object. A companion, NGC 5195. It looks peaceful. More than that, it looks composed, like a painting someone made on purpose, like a jewel that was designed to look exactly like that. Arms perfectly curved, companion perfectly placed, the whole thing lit up and presented to the universe for its appreciation. And in a way, that's the illusion. That's what we need to gently dismantle before we can really understand what we're looking at. Because the Whirlpool Galaxy is not peaceful. It is not composed. It is not the result of some gentle, orderly process of spiral arm formation humming along in quiet astronomical routine. What you're looking at when you look at M51 is the aftermath, the ongoing, still-in-progress aftermath of a collision, a slow, grinding, gravitationally catastrophic encounter between two galaxies that began hundreds of millions of years ago and hasn't finished yet. NGC 5195, that small, fuzzy companion at the arm's tip. That's the culprit. Or, to put it more gently, that's the other participant. Because there are no real villains in galactic dynamics. There's only gravity and time and the stately, patient, enormous processes of things falling toward other things across unthinkable distances. What happened, what is happening, in the slow-motion sense of cosmic time, is that NGC 5195 made a pass through M51, through the disk. Hundreds of millions of years ago, models suggest, the smaller galaxy plunged through or near the main disk of what would become the whirlpool we recognize today. And as it did, it pulled. Gravity doesn't care about scale. Doesn't care that one thing is a whole galaxy, it just pulls. And NGC 5195, falling through and past and through again across those colossal stretches of time, tugged on the material in M51's disk, on the gas, the dust, the stars, the dark matter halo, and in doing so, it sculpted. This is the part that's genuinely beautiful in the most unsentimental way. The arms of M51, those elegant, sweeping, textbook-perfect spiral arms, are, to a meaningful degree, a product of that disturbance. The gravitational interaction with NGC 5195 is understood to enhance the density waves moving through the disk, and it's those density waves, those slowly rotating regions of compression, that organize the gas and the stars and the dust into the clean spiral pattern we see. In a more isolated galaxy, the arms might be patchier, less defined, messier in the astronomical sense rather than the cataloguing sense. The collision sharpened them. The violence gave us the beauty. And there's something worth sitting with in that for a moment, wherever you are. The most iconic image of spiral structure, the galaxy that Lord Rosse sketched by hand in 1845 and became the first human being ever to recognize that some of these faint nebulous objects were not just clouds, but had this extraordinary, organized pinwheeling form. That image, that recognition, that photograph, before photographs existed in the form of an earl's careful pencil marks. All of it is a portrait of a disturbance. A portrait of two things that couldn't leave each other alone. William Parsons, the third Earl of Ross, didn't know that. He was standing in County Offaly in Ireland in the cold, peering through the eyepiece of the Leviathan of Parsonstown, the largest telescope in the world at that time, and he was just trying to see what was there. And what was there was the spiral. He saw it. He drew it. He didn't know it was a galaxy. That understanding would come much later, in the 20th century, when we realized that what we'd been calling nebulae were in many cases entire separate island universes, each containing billions of stars. He certainly didn't know it was in mid-collision. He just saw the arms, and that was extraordinary enough. Charles Messier had catalogued the object decades earlier, in 1773, in his famous list of things that were not comets. Because that was his project, he was a comet hunter, and the fuzzy blobs kept fooling him, kept appearing in his telescope as possible comets and turning out to be something else, something stationary, something deeper. So he made a list of things to ignore when you're looking for comets. And item 51 on that list, M51, was the Whirlpool Galaxy. Not named that yet, not known for its spiral structure yet, just a smear of light in the direction of the constellation Canes Venatici, near the handle of the Big Dipper, that a French comet hunter wrote down in his notebook so he wouldn't mistake it again. And now, more than 250 years later, we know it's a galaxy 50 billion times the mass of the Sun, in the middle of swallowing a companion, home to hundreds of billions of stars, the site of the most distant planet candidate ever detected. Charles Messier's smear of light. You can feel the weight of that, I hope. The way a notation becomes a discovery, becomes a galaxy, becomes a collision, becomes, possibly, a world. Now, the companion, NGC 5195, it didn't just make one pass. The dynamics of these encounters are complicated, and models suggest that the smaller galaxy has been in an extended gravitational entanglement with M51 for a very long time. It isn't a single dramatic event, a single catastrophic collision and goodbye. It's a long, slow engagement. Multiple interactions. The smaller galaxy falling toward the larger, swinging around, being partially captured, orbiting, pulling on the disk again. Over cosmic time, a minor merger like this resolves one way: the smaller galaxy is absorbed. Incorporated, its stars and gas and dark matter fold into the larger system. The process is quiet from the outside, no explosion, no visible drama in any human sensible time frame. But it is irreversible. NGC 5195 is in the very long run becoming part of M51. We call this cannibalism, sometimes galactic cannibalism. It sounds dramatic, and in a cosmic sense it is, a whole galaxy, billions of stars, erased as a separate entity, pulled apart and redistributed, and eventually indistinguishable from the larger structure that consumed it. But consumed isn't quite right either, because the stars themselves don't get destroyed. They just relocate. The galaxy as a distinct, coherent, separate thing ceases to exist. Its parts become something else. And this is happening slowly in Canes Venatici, 28 million light-years away. Now here's where the violence connects to something you might not have expected when we started talking about spiral arms and companions and comet hunters' notebooks. What happens when galaxies interact? Lots of things. The tidal forces disturb the gas clouds, the density waves compress material, and compressed gas does one very specific thing: it collapses. When gas clouds compress hard enough, under the right conditions, gravity wins against the internal pressure and the cloud falls in on itself and a star ignites. Star formation. New stars, triggered by the disturbance, lighting up in the compressed arms like cities appearing along a new road. Those hot young blue-white stars you can see strung along M51's arms in every photograph, those are, at least in part, the children of the collision. The collision is making new suns, and some of those new suns are not ordinary. Some of them are massive, tens of times the mass of our sun. And massive stars live fast and die violently. They don't smoulder for 10 billion years the way our sun will. They burn through their fuel in millions of years, a blink, and then they explode. A supernova. And what's left after a supernova depends on how massive the star was. Sometimes it's a neutron star, an object the mass of our sun compressed into a sphere roughly the width of a city, rotating at mind-bending speeds, the densest ordinary matter in the universe. Sometimes it's something stranger still, a stellar mass black hole, a place where the matter has collapsed past even the neutron state into something that bends space itself into a one-way door. These are the compact objects. And the Whirlpool, seeded by its collision with NGC 5195, with generations of massive stars, has produced many of them. And now we're back at the planet. Because M51 ULS 1b, the candidate, the thing we've been talking about, the 3-hour shadow, the Saturn-sized possible world, orbits one of those compact objects. A neutron star or a black hole pulling matter off a massive companion. An X-ray binary. An ultraluminous X-ray source shining with the energy of hundreds of thousands of suns in X-ray light alone. That system, that violent, strange, extreme system, exists because the Whirlpool Galaxy has been producing extraordinary stars in extraordinary quantities for a very long time. Because NGC 5195 fell through the disk and compressed the gas and triggered the star formation that produced the massive stars that lived and died and left behind the compact objects. The collision made the detector. The same gravitational violence that sculpted the arms and triggered the blue clusters and gave us the most photogenic galaxy in the textbooks, that same violence, followed through its logical chain across millions of years, produced the X-ray binary whose pinpoint glow let Rosanne Di Stefano and her colleagues catch a planet's shadow from 28 million light-years away. The most beautiful galaxy, the most violent one, and the mechanism by which we found possibly the most distant world ever seen. Beauty as violence, detection as shadow, discovery as grief, the grief of a small galaxy losing itself to a larger one, and in the losing, leaving a gift, the extreme stars whose extreme light made the impossible possible. You can rest in that a moment. No need to hold all of it at once. Let it drift. So let's talk about what this means for the map. When Rosanne Di Stefano's team published their paper in Nature Astronomy in September 2021, there were more than 4,000 confirmed exoplanets in the catalogue. Now that number has crossed 5,000. 5,000 worlds, some rocky, some gaseous. Some orbiting in the habitable zones of their stars, some blasted by radiation or frozen in permanent darkness, some so close to their host star that they complete an orbit in hours. 5,000 worlds, and not one of them, not a single one, lies outside our galaxy. Every exoplanet we have ever found, every planet candidate we have ever catalogued, every world we have ever detected by any method across the history of astronomical science has been in the Milky Way. Most of them within a few thousand light-years. A handful scattered a bit farther out. But all of them here. All of them ours, in the sense of belonging to the same enormous disk of stars that our sun is embedded in. The Milky Way is a big place. Don't let me make it sound small, it isn't. It's roughly 100,000 light-years across, containing somewhere between 100 billion and 400 billion stars, and if you were to travel at the speed of light from one side to the other, the journey would take 100,000 years. It is vast beyond any useful human intuition. And yet the universe contains hundreds of billions of galaxies. What we knew about planets before this was essentially a single data point. One galaxy, one population, one neighborhood in the cosmic sense of the word, the Milky Way's planets. Full stop. M51 ULS 1b, if it's real, changes that. 28 million light-years. Think about what that number actually means in terms of scale. The nearest large galaxy to us, Andromeda, is about 2.5 million light-years away. Already that's a distance so large it swallows all ordinary intuition. The Andromeda Galaxy is so far that the light arriving at your eye right now left it when our own ancestors were barely recognizable as anything you'd call human. And Andromeda is our neighbor, our cosmic next door. M51 is more than 10 times farther than that. Every exoplanet we'd ever confirmed is within a few thousand light-years. The closest known exoplanet, Proxima Centauri b, orbits a star just over 4 light-years away. M51 ULS 1b would be roughly 7 million times farther than that. 7 million times farther. We would push the boundary of the known planetary universe by a factor of about 10,000 in a single step. That is not a refinement, that is not an extension, that is a completely different thing from what we were doing before. Finding a planet in the Milky Way is, in some sense, like exploring the block you grew up on. Finding a planet in M51 is like receiving a postcard from a continent you'd never known existed and had no ships to reach. Same postcard. Same writing. Same undeniable evidence that something is there. And yet so far away that far away becomes almost a meaningless phrase. You need a different kind of language, and even then the language keeps failing you. And we haven't confirmed it. This is the part that requires a certain kind of intellectual honesty, and the team offered it, which is worth admiring. Because in September 2021, when the paper came out, the temptation must have been enormous. You've looked at this data. You've seen the light curve. You've applied every test you can think of and ruled out every alternative explanation that leaves a physical signature. The dip is grey, no color change, which rules out a gas or dust cloud. The dip is symmetric, which is consistent with a solid object passing in a clean arc in front of a point source. The dip is total, or very nearly so, which is what you'd expect if a roughly Saturn-sized body blocked a region of X-ray emission small enough to be completely covered. Everything points the same direction, and it's the most extraordinary direction in the history of planetary detection. And they published it as a candidate. Because the honest answer is, it's one event. One transit. And there's a reason astronomers require multiple transits to confirm a planet using the transit method, because a single dip can have other explanations. Natural variability of the source itself, an unfortunate line of sight coincidence with some other intervening structure, something undetected, unexpected, currently unknown. You can argue against the alternatives you've thought of. You cannot argue against the alternatives you haven't imagined yet. And there's one more thing, the thing about the 70 years. If M51 ULS 1b is real, if it's a Saturn-sized planet orbiting tens of astronomical units from its host, farther out than Saturn orbits our Sun, then its year is long. Its orbital period, the time it takes to complete one circuit, is probably measured in decades. Some estimates suggest 70 years or more, and a transit only happens when the planet crosses exactly between us and the X-ray source. once per orbit, which means if the next transit is 70 years away, the next chance to observe this event, to rerun the data, to look again and say, yes, there it is again, that chance won't come until the 2090s. There are astronomers who published this paper who may not be alive when the verification opportunity arrives. That's not morbid, it's just the math. The math of planetary orbits and human lifespans colliding at an awkward angle. The discovery was made now. The confirmation would require then, and then is very far away. So we live with the candidate. Not as a failure and not as a frustration, but as the honest, precise, carefully calibrated status of a genuinely extraordinary observation. Something passed in front of that X-ray source in M51 in data captured by NASA's Chandra X-ray Observatory. Something roughly the size of Saturn. Something solid. And we don't know what it was, with the certainty that science properly demands, and we may not be able to know for a very long time. That's not nothing. That's something. A very specific, very remarkable something. But let's go somewhere with that uncertainty rather than resting in it uneasily. Because the thing about this detection method, the X-ray transit, the tiny source, the total eclipse, is that it's general. It's not a one-off trick that only works for one specific configuration. If it worked for M51 ULS 1b, it can work for other X-ray binaries in other galaxies. And there are a lot of other galaxies with a lot of X-ray sources. Chandra has looked at many of them. XMB Newton has looked at many of them. The data archives from decades of X-ray astronomy contain millions of observations of compact objects in nearby galaxies. How many shadows are hiding in there, unnoticed? How many times has a planet passed in front of an X-ray source while a telescope was watching and nobody looked at the light curve carefully enough? Or the dip was attributed to variability? Or the observation window was too short to catch the whole event? There could be more. There could be many more. The universe is not in the habit of producing exactly one of anything. One galaxy, one star, one planet, one possible transit detection. It tends, when it makes something, to make it abundantly. And if there's a planet orbiting an X-ray binary in M51, then there are almost certainly planets orbiting X-ray binaries in NGC 5195, and in Andromeda, and in the tens of thousands of galaxies reachable by a sensitive X-ray telescope within 100 million light-years of us, and in the billions beyond that. Planets in other galaxies. Worlds made of the same elements, obeying the same physics, built from the collapse of the same kind of gas clouds around the same kind of stars, in places so far away that even light takes millions of years to cross the distance between us. Planets we will probably never see directly. Planets we will probably never know the surface temperature of, or the atmospheric composition of, or the color of the sky of, if they have skies, if they have surfaces. If they have anything we'd recognize as a thing a planet can have. But planets, worlds, things orbiting suns, in other galaxies. The possibility of that, the sheer, vast, almost incomprehensible possibility that the universe beyond our galaxy is not a lifeless arrangement of stars, but a space filled with worlds, with the same planetary diversity we're only beginning to map in our own galaxy, that possibility exists now in a way that it didn't before September 2021 in the same concrete, observationally grounded way. It's not just that it seemed likely. It seemed likely before. Physically, theoretically, statistically, it seemed nearly impossible that our galaxy should be the only one with planets. But now we have a data point. One possible, candidate, provisional, honest, unconfirmed data point that says Something was there. Something transited. Something cast a shadow from 28 million light-years away, and we caught it. That's a different kind of knowing. And you know, wherever you are right now, lying in the dark, or half asleep in a chair, or resting with your eyes closed, hearing these words drift past, you know that you are on a planet. You don't need to think about it. You don't need to verify it. You feel it in the weight of your body, in the pressure of wherever you're resting. Gravity pulling you gently down, the way it pulls everything, the way it pulled NGC 5195 into M51's embrace millions of years ago, the way it holds every planet in every orbit of every star, in every galaxy of the observable universe. Gravity is the great unifier, the one force that never stops working, never takes a break, never has an off switch. And right now, perhaps, on a world orbiting a dead star in the Whirlpool Galaxy, there is something being pulled down by gravity too. We don't know what. We can't know what. The planet, if it's there, orbits a neutron star or a black hole, which means it survived a supernova. Whatever that means for the surface of a world. It's surrounded by X-ray radiation and the fierce, violent flux from the accretion disk of its host. The conditions there are not like ours. They couldn't be. And yet, a planet is a planet. A world is a world. The same physics that assembled this rock we're riding around the sun assembled whatever that thing is out there, if it's there, circling its impossible sun in a galaxy that a comet hunter barely glanced at in 1773. You and it, whatever it is, held down by the same ancient force. That's not nothing, either, it's actually quite a lot. Let me bring you back to the beginning for just a moment, before we close. Because we started with a shadow. That's the thing I keep coming back to. The shadow. In the history of planetary detection, the standard story is one of light. We find planets because of what they do to light. They dim it, they tug on its source and shift its wavelength, they occasionally reflect it. Light is how we see. Light is the medium of astronomical discovery. Even with radio telescopes, even with gravitational wave detectors, even with neutrino observatories. The dominant language of astronomy is photons, but M51L's 1b was found by absence, by a light that stopped, by 3 hours of nothing where there had been something, by an X-ray source that blinked out, quietly, completely, symmetrically, without any change in color, and then returned. The planet, if it's real, made its announcement not by shining, but by blocking. Not by being seen, but by preventing seeing. There's something in that that seems almost philosophical, and I don't want to push it too hard, because the science is strange enough without adding unnecessary poetry on top. But there is something worth noticing about the idea that the most distant world we have evidence for announced itself by going dark, by being exactly opaque at exactly the right moment. By being in the way. Rosanne Di Stefano and her team at the Harvard-Smithsonian Center for Astrophysics were not looking for a planet. They were studying X-ray sources in M51 using Chandra data. They were cataloguing, monitoring, doing the patient work of characterizing a population of unusual objects in a galaxy 28 million light-years away. And in the data, there was a dip. A 3-hour dip in one specific source, designated M51Ls1, an ultraluminous X-ray source, one of the brightest compact object systems in the galaxy. The dip was total, or very nearly so. The flux went to 0, and then it came back. That dip is, as far as we can currently tell, the most distant planetary signal ever detected. inferred from data captured by a telescope that cost billions of dollars and was launched in 1999 on a mission to look at the hot, violent, X-ray bright universe. A telescope built to study black holes and neutron stars and supernovae remnants and galaxy clusters, the universe's most extreme objects. And it caught a planet's shadow by accident, in the sense that by accident means while doing something else entirely and paying close enough attention to notice. That's how science often works. The dedicated, careful, unglamorous work of looking. And in the looking, finding something that wasn't there in any list of things you were looking for. 28 million light-years. A shadow 3 hours long. A world we may not be able to confirm for 70 years. And a beautiful spiral galaxy whose beauty is the record of an act of violence that set all of this in motion long before there were any eyes to see it. If you're still with me, thank you. This slow little journey has taken us a long way from anything ordinary. And if you drifted off somewhere in the middle, that's perfectly all right. The whirlpool is still there, and it will still be there when you wake up. If you've enjoyed spending this sleepy hour with the most distant possible world, and the galaxy that ate a neighbor, and the dead star that might be someone's sun, a quiet like or subscribe would mean a great deal. Small creators like this one rely on your support to keep these nights going. And this channel genuinely does run on it. So if you feel moved to, that would be a lovely thing. And tell me where you are tonight and what time it is in your corner of the world. I'm always glad to know. But now, close the gap. Let the whirlpool spiral away from you. 28 million light-years of distance doing what distance does, making things very small and very still. Let the X-ray binary dim. Let the candidate planet, M51ULS1b, possibly Saturn-sized, possibly orbiting a dead star, possibly real, carry on in its long, unhurried arc around a sun that isn't a sun in the way we usually mean that word. It will be there next year. And the year after. And in 70 years, maybe, someone will point a telescope at it again, and the dip will return, and that will be the confirmation, the verification, the yes. You probably won't be there to see it. Neither will I. But someone will. Some future astronomer in a future observatory with better instruments than anything we currently have. We'll look at the light curve of M51ULS1 and see the flux drop to 0 for 3 hours and know exactly what they're looking at, because a team in 2021 had the patience and the rigor and the honesty to write it down and call it a candidate and say, this is what we saw, and here is what we think it means, and here is everything we cannot yet prove. That's the gift of the data. It waits. The universe is under no pressure to hurry. It has been doing this for nearly 14 billion years and has at least that long again to go. It can wait for the planet to come back around. It can wait for the instruments to improve. It can wait for the confirmation that may take longer than any of us will live to see. The universe waits with extraordinary patience. And in the meantime, it just keeps being itself, colliding galaxies and dying stars, and long orbits and shadows crossing X-ray sources, and gravity doing its quiet, ceaseless, unifying work. And right now, wherever you are, gravity is doing that work on you. Holding you still, holding you down, making this moment, this warm, ordinary, improbable moment of a person resting in a room on a rocky world in an unremarkable arm of a spiral galaxy feel solid and real and enough. You are, in the full literal sense, made of the universe. The calcium in your bones, the iron in your blood, the carbon in every cell, all of it forged in stellar interiors, expelled in stellar deaths, scattered across space, gathered by gravity. assembled over billions of years into the precise and specific configuration that is you, lying here, at this hour, in whatever comfort you've managed to arrange. The same process, the same elements, the same physics, everywhere across 28 million light-years and more. If M51 ULS 1b is real, and we don't know, and we may not know for a generation, then it too is made of that same inventory. Atoms that were forged somewhere, expelled somewhere, gathered by the same patient gravitational pull, assembled into a world, orbiting a dead star, in a galaxy that is slowly consuming its neighbour. 28 million light-years from here. Not so different, not so strange, just very, very far away. Let it go for now. Let the whirlpool spiral back into the dark where it lives. Let M51 ULS 1b, candidate, unconfirmed, extraordinary, continue its long orbit in whatever year it's currently experiencing in that distant spiral disk. Let Lord Ross's sketch fade. Let Charles Messier's notation rest. Let Rosanne Di Stefano's paper sit quietly in the archive of Nature Astronomy, waiting for the 70 years to pass. And sleep, if sleep is where you're going. Or just rest. In the weight and the warmth of being exactly here, exactly now, on a world that is definitely confirmed, definitely real, and, given everything, a pretty extraordinary place to spend an evening. Close the books, dim the lamp. Class is over. Sleepy scholar.